Okay, let's look at the Lagrange equation of motion. Here is the Lagrange operator. It is kinetic energy minus potential energy. And here is the equation of motion in the coordinate system S. But let's look at another coordinate system, S prime. So then you have another expression here. How does the Lagrangian look in the prime system? L prime, T prime minus B prime. And the question is, the equation of motion in that system, is that also the form conserved? So prime coordinates here. So this looks just the same, but the prime coordinates instead. Okay, just look at the scaled and translated frame S prime. So x prime equal a constant times x plus b. The b is the translation, a is scaling. And from this, we can see that vx prime, the velocity, is just a times vx. And here is the Lagrangian, and here is the Lagrangian in the prime system, depending on x prime and vx prime. But that is nothing else than the Lagrangian where we change the coordinates from x instead into x prime. It's a dependence, obviously, as you can see here. And also vx, how is that depending on x prime and possibly vx prime? And let's evaluate this term here. It's coming from here. So then you can show that this is just del dvx and 1 over a here. And that comes from this one here. Obviously, it has something to do with a when we're playing with the derivatives, the partial derivatives. So you get this. And the question is, okay, will we preserve this form here? We look at this, okay, and this we just calculated here, 1 over a, and then you put it in here, and you get this, because this factor here is nothing else than this, and in S system, so that's the LDX. So that's what we write here, and then we look at that one, the term here, dl prime, okay, and it turns out you get exactly the same, 1 over a dldx, like this, and this minus this is obviously 0. So in fact, for this transformation, we actually showed that the form of the equation of motion is exactly the same. And this turns out to be a general result.